So Jessica's here, we can start.
Yeah, no, I think we can start and the others can watch the video or catch up. Yep. So that'll be fine.
Okay, well, good afternoon to everybody here and those who are watching asynchronously. This is the third part of the Promises and Perils of AI. And I told you scary stories, some interesting stories, but we're going back down to earth right now. And first I will remind you what we talked about. We basically talked about AI and this resurgence of AI, and I explained why. Because of these three factors, we have a lot of data, more than ever before. And we have powerful computers today. And also thanks to these powerful computers and the data that we have, now we can experiment with sophisticated algorithms. I also talked about the use of machine learning in precision health. And that led to an enumeration of many applications. I also talked about achievements in AI from Deep Blue to AlphaGo. And finally, I talked about the three paths to the singularity, so my view of that. And I particularly insisted on the third one, which is the cybernetic singularity, because I believe in that. Doesn't mean that I'm in favor of that I encourage that, but I believe that that's one path that could lead us to what we call singularity. By the way, recently there's a debate that is happening online. One person, important person actually in the community, has claimed that computers have reached some kind of consciousness. And he said that there's some slight consciousness that is happening. And of course, many people are against it. There's a debate happening currently online. This tweet came up, I believe the 9th or the 10th of February. And of course, many people are not agreeing with that. And the interesting thing is that actually we don't know how to define intelligence. How to define consciousness is even more complicated. And now in that debate is interesting because people are talking about when do children that just born start having this consciousness, and how do animals have consciousness? So it's very vague. It's not a clear kind of definition. Anyways, I talked about AI and computational intelligence. It's not artificial intelligence. I prefer using the term computational intelligence. It's an intelligence that is computed. And I said that there are two reasons why people are doing this. One of them is also to understand how we are functioning. The machine, the human machine, is how are we intelligent? So this is obviously not new. Philosophers have been discussing this for a long time. And there is, this is something I didn't cover last time at the lecture. There's a test that has been around for a while to test if a machine is intelligent or not. And this is called the Turing Test, because Alan Turing was the first to come up with the idea. He suggested it in an essay that he wrote in 1950, Computing Machinery and Intelligence. And in that, that test is based on a game called Imitation Game. It's interesting because it's kind of a sexist game. Originally, it was to have somebody guessing whether it's a female or a male talking behind the curtain, but he changed it. It changed it to you have a person behind the curtain and two others on the other side or whatever, and he's communicating with these people, and that person, if he or she doesn't know if the entity or the person behind is a person or a machine, then that machine is actually intelligent. So I'm conversing with something behind the curtain, and if I can't say if that something is a person or not, then if it is a machine, then the machine is intelligent enough to make me believe it's a human. So here how it is. So you have this human interrogator and you have a human and a machine. And if this interrogator doesn't know whether it's talking to a human or a machine, then that machine is intelligent enough. And this is what we call the Turing Test. And this led to many interesting work about building these chatbots that could chat with a human, and then the human doesn't, well, they're trying to fool this human to think it is a human, not a machine talking to it. One of the first, or the first chatbot that was created was ELIZA by Weizenbaum at MIT in 1966. And ELIZA is still around. Actually, the MIT school has a simulator of the original ELIZA that is still online. You can go and try it. It is simulating a psychotherapist who is answering statements. You can see ELIZA and a person here talking, and it is based on some very simple rules, taking some cues from the sentence that the human has said and repeating them differently and enticing the person to keep on talking. Interestingly, when this was released in 1966, this new one was in 2005 and improved upon later. But when they decided to turn it off, many people complained. They said, no, we actually like it. We want to talk to this ELIZA. But ELIZA wasn't particularly smart in the sense that we knew that it was a machine. And even if you put it behind a curtain, we know it's ELIZA, not a human. But this led to competitions where every year people tried to fool real judges. And there was a prize, the LABMP award, $10,000, who can fool a judge for at least 5 minutes. Why 5 minutes? Because Alan Turing, and I go back here, he said by year 2000, a machine might have a 30% chance of fooling a lay person for 5 minutes. So the competition was to try to fool at least one of the three judges for at least 5 minutes. And for many years, there was this competition. I'll show you some examples. They're ridiculous. It's obviously a machine, not a human. Well, we know it's a machine and not a human behind the curtain. So it was very difficult to fool the judges. I'm showing you some examples. In the beginning, it starts very well. This is Jabberwocky in 2003, was placed third, was placed fourth also in 2008. You see the conversation is still okay, but at one point it starts going in a very bizarre direction here. And this is real. This is me trying to, I was trying Jabberwocky. Here's another one. Alice is a very good one. Won the prize a few years in a row. Still around. You can also try it. Here it starts, here I'm Alice, where are you? I'm in Auckland, California, where are you? It's asking me, so that's cool. Yeah, I'm in Canada. Tell me a little about life in Canada. It's cold. I am warm here. That's nice, seems intelligent. And I asked, where's the best Chinese restaurant? I think it's a Thai. And then it starts going south. It doesn't make any sense anymore. So it doesn't last 5 minutes before you realize it's a machine, okay? So these are really bizarre kind of answers. It's hallucinating, we say. It's going in a different direction. Here's another one, Cleverbot. And these are the best of the best. Oops. Hello, where have you been? I missed you, but I've never met, and blah, blah, blah. So it it has these canned kind of sentences to provoke you. And then from time to time, it starts hallucinating. In 2000, when was it? I forgot exactly, but a few years back, somebody won the LABMP Prize because they pretended, so they fooled 29% of the judges for 5 minutes. They pretended to be a young kid, a 13-year-old boy from Ukraine. So yeah, a little bit more indulgent. This kid doesn't know everything, and oh, it's a foreigner, so even if it makes mistakes in English, it's fine. And that's how they fool the judge. This is an example of a discussion you have with it. I'm going to go quickly here. That was in 2014, and now the prize is over. I mean, the competition is over, and people don't believe very much in this test as much as they used to, because actually you can fool humans very easily. It's not having the goal is not to have a conversation anymore. The goal is to fool the other to believe that you're a machine. And that's a different objective. But now we are familiar with many of these chatbots like Alexa, Siri, Cortana, and many, many more. You have to realize that these are not real chatbots. They are what we call task-oriented chatbots. So they use machine learning to detect your intent. What is your intent? And based on the intent that they detected, they have what we call a template, and they follow the template to fill in some what we call slots. For example, they detect that you want to make a reservation in a restaurant, then there's a template for it. And the template has questions of how many people want to go to a restaurant, when, what kind of food, how far, and things like that. So that has this discussion to fill in these slots in order to build a query that goes to a database and it does the reservation for you. Same thing if it detects that you want to know the temperature, or you want to buy a book or something like that. So it's a question of detecting intent. It's not an open-ended kind of conversation. Here at U of A, we're working on an open-ended conversation. We're not the only ones, of course. There are other people who are interested in that. And in our case, we are targeting building a chatbot for the elderly as a companion, because many old people decide to stay at home instead of going to a nursing home or something like that. And they're alone. Boredom is bad for their mental health. Now we understand it with COVID confinement, but it's a reality for many elderly. And so companionship is something that, well, we'd like to have a human, but we don't have enough human to go to all these houses. So if we can simulate that with the chatbot, that'd be great. Here's an example of a discussion. It's still far away from humans, obviously, but the idea is to be able to detect emotions and be emotionally intelligent, meaning responding to that emotion with emotion, detecting also humor, which is extremely difficult. I'll show you an example where we're trying to have humor. I said, this is me talking and this is Anna talking. Anna is the chatbot. Two silkworms had a race. They ended up in a tie, and this is our chatbot trying to detect something that doesn't make sense, nonsensical sentences, and it detected that this doesn't make sense. Instead of detecting it's a joke, and it says worms don't race. It's a joke. I know. Okay, did you get it? Silk and tie? Not really. So. But then, actually, humor is a very complex thing. And I don't know if animals have the notion of humor, but for humans, it's actually a very complex manifestation of intelligence. So here's the conversation continue. I said, I will give you another one, meaning another joke. And this answer that it's not canned, it's really generated randomly. Well, not really randomly, it's based on the context. And you realize, oh my gosh, it's actually understanding me. Then I give it the joke, another joke that you can read by yourself here. but it didn't realize again that it's a joke. It says, it's disgusting. So it's still very hard to have kind of conversations like we're doing. You can try it with Siri and you'll see how fun it is. The other thing that we talked about is the fact that deep learning, remember deep learning is part of supervised learning, which is part of machine learning, which is part of AI. So what I would like to talk about today, this is why I said back to earth, I want to focus on supervised learning and machine learning in general, and show you how this is done. How does a machine actually learn some task? And so I'll be talking about what we call supervised learning. Supervised learning means that I supervise the machine by giving it examples, giving it some training. I will train it. And the metaphor that I often use to show this, to illustrate this, is the following. I have a pile of balls, and these balls have different shapes, different sizes. Well, they're all balls, but they have different structures. Some have they're rough, the other one are smooth, and different colors, different weight. So different features, basically. And then I have in front of me a certain number of buckets. The buckets are colored, so they're labeled. And these represent my labels, my classes, actually. And then I have a child next to me, and I say, hey, watch me, what I'm doing. Watch and learn. Okay, and then I grab one ball at a time. I look at it, and then I place it in the bucket. Grab another ball, look at it, assess it, place it in the bucket. What am I doing here? I'm actually showing the decisions that I'm making for each of these balls. And the child watching me, if the child is smart enough, and they will very quickly realize, they build a model, realizing what makes me decide to put it in this bucket or the other bucket. So at one point I can give a ball to the child and say, it's your turn, and the child will be able to put it in the right bucket. What did they build in their mind? It's a model that allows them to predict, giving a particular ball, which bucket I should put them in. And they will realize it's not the weight, it's not the size, it's not how rough it is or whatever. It's actually the color that made me decide in which bucket I put it in. Okay, and that's the predictive model they built. Well, machine learning is exactly the same. Supervised machine learning is exactly the same. What you do is you provide training data that has already been labeled, and the algorithm will go over that to try to identify the features that discriminate between the different classes, and it builds a model. What is this model? It's a classification model that predicts, given some features, which class this object falls into. And now I have new objects that have never been labeled before, never been seen before. And well, I'll put a face on this model to make it more sympathetic here. And I'll use that model to predict the labels automatically. Okay, how can I use this? Well, you are using this already day after day without knowing. For example, when you use your email, you delete some email, you read some email, you save some email, you answer some email. That's the training. The system built in within the email client learns to predict what is the email that is actually considered spam that you will not read, and what is the email that actually is important, based on different features, not just the words inside, where it's coming from, what time it was sent, and all different features. So observing you, I will build a model, and that model is used to automatically label the new email that has never been seen before and put these in the spam folder automatically. Okay, I can use it also with, for example, mammography. I have mammograms here that have been annotated by a specialist, and then the program will go over that and builds a predictive model, and that model will be used to automatically label new images that haven't seen before. Okay, these techniques actually are now performing better than humans. There are many particularities of this framework. Well, it's not solved by all means. I mean, these are still open problems at many levels. For example, when I have this data that is labeled, what are the relevant features to be considered in this algorithm to put in the model? What is the best algorithm, optimal algorithm to go through this efficiently and effectively to build this model? And this model, how do I represent it such that I can use it properly when I am doing this classification automatically? There are so many different aspects that have to be taken into account. But overall, it works very well, and it has been applied in many applications, whether it is for autonomous vehicles, recognizing different road signs, or recognizing if there's a line on the road, or is it the edge of the road, or is it a pedestrian crossing in front of me, or a plastic bag flying, or so all these are actually a set of different supervised learning algorithms that are recognizing all the different things. And handwriting, I think I mentioned one early program that recognizes the digits for the, for example, the postal code on the envelopes or the numbers on the check that you write. Well, this is using machine learning that was trained on different handwriting, and now it recognizes the 2 from the 3, the 3 from the 8, and so forth. It can also be used to recognize mathematical formulae that is handwritten and then write them properly, or even handwriting like this, and then you have them built-in tablets today. We use them, we don't realize, but behind the scene, that's machine learning. Spam filters, I mentioned, credit card fraud detection, detecting fraud for credit card transactions, but also in financial applications, especially when we're dealing with high frequency trading. Humans cannot check all that. So it's all done by machine learning. Approval for credit, recommender systems also use a lot of machine learning. A typical one is for predicting which movie you will watch next, or which book will you read next, and things like that. So we have this big matrix where we have all the possible movies, let's say, and all the possible people that have already saw these movies, or these, let's fix on, say movies. Okay, so I have all the movies and I have all the people that watched these movies and rated them. And there's you as well, and you rated some movies, but all the other movies you didn't rate. Not all movies are rated by everybody. Not everyone is rating all the movies. So it's a very sparse kind of matrix. And the recommender system would learn from all the ratings that exist to predict the other ratings that are missing. And then it predicts for you what is the highest rating that you will give to any of these movies, and it will recommend the movie that you have the highest rating for, that it predicts that you will have the highest rating for. So it's all based on this machine learning. Adaptive interfaces, whether it is online, like an interface or user interface on the screen, like on Facebook, for example, or it can be even a remote control for TV. It learns what are the channels that you like watching and the channels that you want to skip, and it will skip them automatically for you. You don't have to program it yourself. It learns from you. I don't remember if I mentioned also this hat that has these sensors, and it can detect the brain activity when you're thinking about moving this arm or moving this finger or moving this leg. So somebody who's paraplegic, we can ask that person to think about, they cannot, but they think about moving their leg or their toe or whatever, and then we learn to detect that and associate it to movement of the wheelchair or movement of the cursor. And there are many applications in healthcare. I don't know if I mentioned all these last time. For me, it's like a deja vu. So I don't know if I covered it with you. So what we do in healthcare, for example, is I have a patient, I have some information about that patient, and I need to predict something. How do I learn? Well, I have historical data, other patients, each row here is a patient, and I have information about what I want to predict for that patient. I have information about the other patient. So I can use this as the label. This is the color of the buckets, for example, and I will build a predictive model, and that predictive model now will use this information, new patient, to predict this missing information for it. Okay. Now there are different kinds of problems. There's the case here where I have many different labels. This is the case where we have a multi-class classification. So I need to classify something in different buckets, one of these buckets. But most problems are actually binary classification. I have only two classes. Is it spam or non-spam? Is it fraudulent or non-fraudulent? Is it cancer or no cancer? The algorithms that go through this data to learn a predictive model are different. There's also the case where once I build the predictive model and I have new data, each element is put in one class only. And this is called the single label classification. Each one gets only one label. But there's some problems where each object can get more than one label. So imagine here, I don't know, I have a report from a radiologist, and I need to say, okay, what they're talking about this disease or that disease in this medical image. Well, they can talk about two. Same thing as the email about this topic or that topic. Well, it's many topics. This image is about, does it have a lion or a cat or a dog or an elephant? Well, it can have an elephant and a lion, both. Okay, so I can have multi-labels per element. So this is called multi-label classification. Also, another very important notion, particularly for the case of precision health, when you use machine learning in precision health, when you learn this model, that model is often a black box. So the predictive model works fine. It can be very highly accurate. But when you ask it, why did you predict this or that? It cannot explain. There are other models that once it goes through this data, it will generate a transparent model, transparent in the sense that I can see what it has learned. And in this case, I'm representing them by rules. If I have feature A and feature B, then it should be class green. If it's C and D, then it should be class gray, and so forth. So not only I can see inside and see why it predicted this class or that class, but I have the potential to actually edit this model. If I have extra knowledge that was not expressed in the training data, but I don't know, I'm a doctor who has seen these other cases, I can change these rules. And this is very rare, unfortunately. Most of the very efficient and effective classifiers are unfortunately black boxes. There's another important notion, is this notion of imbalance. So most of the techniques that exist assume that in the training, you give the same chance of one class or the other to be represented. So we have what we call a balanced data set, balanced training set. And the classification, the model that is built here assumes that there's this balance. But in reality, in many cases, we have an imbalanced training data. The data that we obtain to train the model is completely imbalanced. There's one class that is represented way more than the other class. One class is a minority, the other one is a majority. So obviously the predictive model will be biased towards the majority class. And that's a problem. So one is called imbalanced, one's called balanced, and there are techniques to handle this imbalance if you know about it. Either you adjust the data before you learn, or you inform the algorithm to deal with the cost. So the imbalance is not only for the number of representation, also can be the cost of misclassification. If I misclassify, for example, mammography and say, this woman doesn't have cancer, while she has cancer, the cost is death. or potential death. The cost of the other misclassification, a woman doesn't have cancer, and I say, well, she has cancer. Well, there's a cost too. It's a biopsy and psychological problems, but hey, there's no death. So the costs are not the same. The imbalance can be the cost or can be the number of representations. Okay, so what I wanted to say here, what you need to remember is that there is an input. There are two phases. The first phase is an input is the training data, and then the output is the classification model. The second phase, the input is the classification model and some evidence, and the output is a label on that evidence. Okay, so then there's a framework under which we build these classifiers. You get data that is labeled, very expensive to obtain. Then you split it into two sets, one set that we will use for training, and one set we leave aside, holdout. This holdout is used after we build our classifier, this model here. We will estimate the accuracy by looking at how it performs on the test data. Okay. Once the accuracy is acceptable for deployment, then we deploy it, and then we have new data that is not labeled, and we label that, and we can trust it because it worked well with the test data. So with this framework, there are many, many techniques that exist. These are families or paradigms for learning. I will only cover 3, and I chose them on purpose because they're completely different, yet their goal is exactly the same: how to build this predictive model. So the first one is the simplest one. It's so simple that actually there's no learning whatsoever. It's fake. We call it lazy learning. I'm not learning at all. So what happens is that I'm giving this training data. The only thing I do is I may sort it or something, put it aside. That's what happens in phase 1. Now, when I'm giving a new object that I need to classify, I need to label, basically what I'll do, I'll look at my training data and say, which one is the closest to this one? Nearest neighbor. And the one that is the closest, some function of similarity, they're the closest, then I'll take the label of that one and I assign it to the new one and say, they have the same label. Okay. That's why we call it lazy learning. So here I have my data, the training data. I'll leave it aside. I'm not learning anything. Now I have a new object. When I have the new object, I will use a distance function to find among these who is the closest to this guy. Oh, here it is. So I will take the blue color. I have blue and red. These are the two classes. So one could be cancer, the other one is no cancer, for example. And I will assign this label to this new object. This is very, very kind of lazy learning. There are variations to this. One of them is, why do I take the nearest neighbor? Why don't I take the k nearest neighbors, the 5 nearest neighbors, or the 3 nearest neighbors, or the 10 nearest neighbors? So this is the other version, the k nearest neighbors. K can be any number. I have a new object, then I'll take the k nearest neighbors. Well, they may not all agree on what the outcome is, so what class it is. Then they will vote. So I'll do a vote, and the majority will win. So that's one approach. There are other approaches, particularly when I have, I can do also weighted approach. So it's not a vote, democratic kind of vote, it's a weighted vote. Some will have more than others, and the weight could be based on the distance that I have between this object and these nearest neighbors. There's another approach that is dealing with the size of the training data. So if I have too many of them, each time looking who's the nearest neighbor takes a long time. So instead, I will cluster them in groups, in partitions. And for each partition, I will have a representative. And then I will look for the nearest representative neighbor. And I'll do a vote as well, same idea. Okay, so that's for nearest neighbors. Before I continue forward, is there any question about this approach of learning? It's very lazy learning because I didn't do anything except organizing them here. No? Okay. So I'll show you another approach, which is instead of putting this training data aside and waiting for somebody to come to me and say, hey, predict the label of this. And by the way, just as an example, to better understand how k-nearest neighbors works, imagine I have, these are emails. Some emails, you put them in the spam, some emails, you didn't put them in the spam, you answered them. And now I have a new email coming in. I will look at where is the closest email that you had in the past, and did you answer it or did you dump it? And this is how I will decide whether I'll dump it or not. Okay, I hope this is clear. But that means I have to store all the emails. It's not very good. It's better to have a representation of that knowledge. And this is where learning actually comes in, because the other one, as I said, is lazy learning. I'm not learning anything, I'm keeping all the data. Here, I'm learning some kind of representation of the knowledge inside that training data, so I can use just that representation to make my predictions. So imagine here I have data where I have information about the weather. And here I have information about whether I played or I didn't play tennis. So this is data. This is data that I got from a paper that was published in the 80s by the guy who, Quinlan, who introduced the idea of decision tree induction. So this is where when he played tennis or didn't play tennis, whether it's windy, humid, there's temperatures high or low or medium, and then the outlook, is it sunny, is it covered with clouds or whatever. So based on this information, this is the observation that we had before. And now, given another observation of today, what is it today, outlook, what's the temperature, what's the humidity, what's the wind, can I predict whether this person will play tennis, yes or no? Okay. So how can I do this? Well, I can build what we call a decision tree. Like this one here, I can ask, how is the outlook? Because if the outlook is overcast, I notice that each time there's overcast, I play. Overcast, I play. Overcast, overcast, I play. I put on purpose these colors to distinguish between the two classes. So if the outlook is overcast, then I'll play. I can predict it automatically. However, if the outlook is sunny, well, I don't know, because I have some sunny in the red and some sunny in the gray. So then I ask another question, how is the humidity? Because if the outlook is sunny and the humidity is high, I will not play. But if the outlook is sunny and the humidity is normal, I will play. Okay, I'll do the same thing for the rain. So basically this tree tells me, given some conditions, I'll check how is the outlook, how is the wind, and I will tell you here, these are what we call leaf nodes. I will tell you whether I should predict play or non-play. The question is, how do I build such a tree? And this tree is not unique. It happens that I started asking the question, how is the outlook? I could have started asking the question, is it windy or non-windy? And then it gives me a different tree. So how do I build a tree that is not too deep and not too shallow and covers all the cases that I'd like to predict? So as you can see, the prediction is a branch in that, it's a path in that tree. Okay. Well, this is what the algorithm is about. The decision tree induction is an algorithm that will automatically generate in a deterministic way a tree that can predict the best we can, given the training data. So the algorithm is as follows. I will start with the root of the tree. The root is upside down, actually. The root is on top, the leaves are on the bottom. This is how we see trees in computer science. So you put all your training data in the root node and you check recursively. Each time you have a node, you check, are all the data points in my node from the same class? If they are from the same class, that's easy. I will label that node as a leaf node with the class. If not, then I will see what is the attribute that best separates these data points from my node, separates them in two different classes. And I take that attribute and I make it a question for that node. Like I have here the question, what is the outlook, or what is the wind? These are the attributes, okay? Wind, humidity, and so, outlook, and so forth. So I will take that attribute, make it a question for that node, and then I have as many children of that parent as I have possible values. And I distribute my data into these new nodes, and then recursively ask myself the same question: are all the data points in that node from the same class? If yes, I'll label it as a leaf node with that class. Otherwise, I have to find another attribute and split it again. And I stop this recursive method when they're all in the same class. That's when I label it. Or I don't have any attributes to split anymore, so I will label it with the majority class. Or that node is actually empty. There's nothing from the parent data points that have that value for that attribute. The question is, how do I select the best attribute? And this is based on some information gain and information theory that people have used. They use different techniques to choose what is the best attribute, because if you choose a different attribute, you will get a different tree. Okay. So now, once you have this tree, that represents, if you wish, the essence of this data. And once you get a new object you want to predict, you just follow the path, and the leaf node will tell you, is it this class or that class? Okay. Any questions about these trees? No. I don't know how much time do I have. Okay. Now let's talk about the third method. I said I will cover only 3 methods. One is nearest neighbor, and the other one is decision trees. And you see both of them, I have training data, and then it creates some kind of model. Then I have a new object, and it'll predict what it is. So they do more or less the same thing. They don't have the same accuracy, but they do the same thing. Here's a third method, completely different. The 2 others were completely different. They have the same input, the same output, but they're completely different. Here's a third one, it's completely different, and it's based on neural networks, human neural networks. It's inspired, let's say, by how the neurons in our brain function, or we think they function. In our brain, we have about 100 billion neurons, different shapes, actually they may have different functions. What is 100 billion? It's difficult to fathom. I often use the example of a swimming pool, the number of drops you need to have in order to fill an Olympic swimming pool of 50 meters. I mean, it's phenomenal how many neurons we have. By the way, we have about also 500 million neurons in our guts, not just in the brain. We have about, I don't know, thousands of these, 10,000 connections. Each neuron has these connections. So then not only we have 100 billion neurons, but we have many, many, many connections. The difference between these neurons, and I'll tell you about the artificial neurons, is the speed. We are relatively slow. Our neurons are relatively slow to do all these communications. Some of them are electric, some of them are chemical. The computer is way, 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 way faster. But where the brain beats the current computers is in the number of connections. We have so many connections, 100 billion of those neurons. So if I zoom in an artificial neuron, it looks something like this. Basically, I have many signals coming in. Okay, this is like the dendrites in the neuron in our brain. Each one comes with a weight, so they don't have the same weights, and the weights could be negative. Some are exciting the neuron, some are inhibiting the neuron. Okay, so all these signals are coming with different weights. Imagine you have these vectors, and then it arrives here and they are summed up somehow. And actually the neuron, we call it the soma, the body of the neuron. There could be some bias that is added, And this information is given to an activation function. The activation function decides to fire the signal forward or not, along the axon, okay, to another neuron. So it becomes an input of another neuron. So this is just one artificial neuron. But in the artificial brain, we connect them in layers. So you have neurons here that are connected to other neurons on the other layer that are connected to other neurons on the other layer. And these connections have weights, okay? The learning is about assigning weights to these connections. Originally, they start random, but the learning is a process to adjust these weights such that when I give as input on one layer, this is what we call an input layer. Actually, I have it here. I have an input layer and I have an output layer. The information goes forward from the input layer towards the output layer. And each neuron sends the signal to the others. Once the activation function decides to send the signal goes to the next layer and so forth. I put as input the data that I need to label, and I get the label as output. That's the idea. So how do I do that such that I adjust the weights to the point where I get accurate predictions at the end? Okay, this is very similar to, we think, like the neurons, the real neurons. Here's the analogy. As I said, you have dendrites here, and you have the soma here, and at one point this cell will decide to send the signal along the axon. So here's the axon of this one, it goes to the synapse, the dendrite of the other cell, and so forth. Okay, so we have layers as well. This is this notion of layers. That's exactly what is happening here. I have the signal coming on the from the dendrites. This is where the activation function happened, boom, and it sends it along the axon. Okay, so the learning, I have data that is given to me. This is the training data. I will take just the information without the label. I don't give the label, just give the information, I code it through these input layer neurons. The data is propagated along these layers up to the output. And then the output, I will check, is it the output that I desired? If it is what I desired, that's great. If it's not what I wanted, then I will propagate the error back. Going backwards, I will fix these weights such that I will next time get that label that I expected. It doesn't happen in one shot, so there are many, we call them epochs. There's thousands and thousands of iterations until it converges and it will predict the right thing. Okay. The prediction is actually typically quite high. It is very robust to noise in the data, and however, it takes a long time to train. It's very complex to design the network, and it's also impossible to understand what has been learned, because what has been learned are these weights, and these weights, you can't interpret them, so it's a black box. And also later, when it predicts perfectly, yes, it is cancer or no cancer, and you say, why is it cancer? It can't tell you what it is. Now, in the past, we used to engineer these features and pass them along the input layer. Today, with deep learning, we don't have to engineer anything. These features are learned automatically by the different layers of the neural network. And we call it deep learning because we added way more layers in this architecture. Okay. But deep learning also inherits the problems of neural network, namely the time it takes to converge, to learn. It takes a long time, and it's tedious to come up with these architectures. But deep learning is essentially the same as neural networks. We use the same kind of artificial neurons. The only difference is that we have way more layers because the computers that we have today allow us to do this. And there are many different architectures, like the convolutional neural networks. They have the recurrent neural networks and so forth. Okay, so what you need to retain here is that in machine learning, you have training data that is given, where the labels are already given, and there's an algorithm that goes through that to build a predictive model, whether that is some rules, whether that is a decision tree or some kind of data structure, or whether it's a mathematical formulae or hyperplane dividing the different spaces, or maybe a neural network. It doesn't really matter. What matters is that we learn some kind of representation from this data, and that representation is predictive. We will use it to predict for objects that we haven't seen before. Okay, that's what, so it learned this representation to exploit when I need to do predictions. Okay, that's supervised learning. I don't know if I went too fast or I lost my audience, but that's the talk of today. So, well, let's start a conversation.
Yeah. Okay. Any questions? Comments?
Yeah, I kind of wanted to say that I think, like, also for myself, I was very kind of skeptical before with the whole artificial intelligence thing. I think lots of people think of it as like something that is coming to kind of take over us human beings, and, you know, kind of it creates this false narrative. But then, like, you know, you sort of realize, like, also through these lectures that, like, you know, it's just like it says on this slide, it's like it's here to assist us and kind of help us advance in our own projects and sort of just make that advancement as a whole. So I found that really, really interesting.
Cool. No, thank you. Thank you. It is a reality. People like sensational articles, and they write these things and they create this fear. But when you open the box, you realize, yeah, the magic is not what I thought. We're still far away from what they make us believe it is. It's not there yet. Yeah. But we can do amazing things. I mean, when you look at the achievements, it's amazing what we can do today with AI. It's not our equal yet.
For sure. And another thing that I found kind of cool is, like, when you kind of put up those slides of the chats of, like, you know, having those discussions, it was so interesting how, like, you know, you could be having a regular discussion with this robot, and then all of a sudden it just completely goes off topic to this really random, like, dialogue. And it's so weird because, like, you'll be having a normal conversation and then they'll just say something out of the blue, and it's so weird that it works that way. And I don't even know how to, like, process it in my head to explain.
So many of the modern chatbots, or I don't like chatbots, but conversational agents, they are based on what we call a language model. What is a language model? Language model, basically, we go through a lot of text and we learn to predict what word comes after which words. And that is very useful. For example, you're using your phone, you're writing an SMS, and it already predicts the next word, and it suggests it to you. You can click on it rather than typing it. So it's useful for that. But it's all when it goes through a massive amount of data, text data, it can actually learn the language. That's why we call it a language model. And you can start a sentence and it completes it for you. And you can complete different possibilities, and you can rank them, and you select one automatically behind the scene, obviously, and you can build a conversational agents like that. Now, because it learns from a large corpus, and that corpus can be filled with bias. Imagine you're learning from social media. I mean, social media is incredibly biased. It learns that bias as well. And sometimes it starts also hallucinating. You're talking about, let's say we're talking about the weather, and then suddenly it starts talking about pigs and farms. Has nothing to do. It's because it's somehow predicted one word after the sentence, and that word led to another word that is in a completely different topic. So we're talking about grounding the conversational, grounding the output based on some knowledge. We force it to stay on a particular text, or we force it to stay on a particular knowledge graph. We give it a knowledge graph and say, stay here in the topic, don't go away. However, even we humans, when we discuss something, we shift from one topic to another. But logically, I mean, they are related. And we have the capability to go back to topic. We go on a tangent, but then we come back. How to control that automatically in a conversational agent is not trivial. Yeah, and it hallucinates a lot. We have to also detect that it's hallucinating to correct it. And this is something we're working on. Yeah. So having like a Star Trek Data talking to us is, well, still far from that. It's easy to do it in science fiction movies.
So there's a challenge now to build a future world. It's a 4-component challenge. One is to predict the major events 2022 all the way up to 2045. So the applications are due on April 15th, so 2 months from today. And so we're going to do that, a team of us. So it's like building your own world. And, you know, if you think of what things are possible to optimize, a sort of artificial world built only for one person can obviously work. I mean, it isn't difficult, and it can satisfy that person for a long time and so on. So maybe, you know, if you think of the Fermi paradox and why aliens haven't reached Earth,
Contacted us, yeah.
Yeah, it can be that these artificial worlds are so satisfying that you don't want to take a trip. You just want to stay home and play in your own artificial world. Yeah.
Yeah. So it will separate us more than bring us together. Because
Yeah.
each one will be isolated in an imaginary world.
Right.
And that's why people are talking about the possibility that we live in a matrix.
Yeah. Yeah,
Maybe
we could
are
all
in it.
already be there, and so this would just make it slightly better or than it is now.
So
Yeah.
it's one inside the other.
Yeah.
Another virtual inside the matrix.
Then, you know, there's ineffable content, things that can't be put in words. And that, of course, is related to the idea in the future we can communicate via thoughts. So that's going to change everything too, when we're able to send and receive thoughts directly. Yeah.
But how dangerous is that? What if I don't want to share my thought and somebody
Right.
takes my thought?
Right.
And I want to be able to control when to share it and when not to share it, and remember to turn it off when I don't want to share. It adds a lot of complication in this.
Yeah. Okay, well, thank you very much for these 3 lectures, and
Thank you.
Yeah, so we'll see you back. So you've been doing this with us for more than 10 years now. So anyway, yeah.
I had less gray hair.
we have pictures of the first time.
Yeah,
that,
you can put one after the other and see how yeah.
Yeah.
Morphing.
So anyway, follow the progress. Okay, well, you get back 19 minutes of your day then, all of you, so you can see what useful things you can do with these.
Yeah, no, I
Nine-
thank you for that because my day started at 8 and will finish after 6:30. So
Yeah,
this 20 minutes, these 20 minutes will be very beneficial for me.
right. Okay, great. Thank you, and
Thank you,
we'll
guys.
see you
Thank you
next
so
time. Right.
Thank you.
much.
Bye-bye.
Thank you.
Thank
Bye.
you.